All right, correlating my recent whiteboard work with the book, this is 6.2, the mole and the chemical formula. If I start with mole, this is the portion that we are already done with. It explains what mole is, what Avogadro's constant is, how do we define mole. Mole has a mass equal to its relative formula mass in grams. That's just one way of saying it, but that's not exactly the definition of mole. If mole comes as a definition, which it has, in past 10 years papers, you're going to find it like 2 to 3 questions asking simply to define mole. Then the second point in this pink portion, that 1 mole of the substance contains 6.02 into 10 to the power 23, which is, by the way, the Avogadro's constant, number of atoms, molecules, formula units, maybe ions, whatever species we're talking about, depending upon the substance considered, that would be 1 mole. Okay, so that's how you define mole. Now, for the calculations involving the mole, the first way we define mole or calculate it is through molar mass. So that's defined, the formula that we continuously keep going about. The number of moles is equal to mass over molar mass. We also try to do it in a form of triangle. This triangle is actually a very good way of representing it. Now, let me tell you why. Because any quantity written over here, for example, you need to find number of moles. The other two quantities, take a look at this. The central portion gives you the idea what to do. So you need to divide mass over molar mass. That's one form of the formula. Let's rearrange the formula. Let's suppose you're supposed to find molar mass, which you're most commonly are able to do from the periodic table. But what if it's an unknown element or unknown material? If that's the case, which is going to be, for which you're going to see past paper questions as well, since that has happened a few times in past paper questions. So you need to find this. So it is pretty easy. This is the boundary line for these two, and that's how it's going to go. Mass over number of moles. Division, right? It's a great diagram actually. Coming back to the third one, if you need to find mass, and then you have the other two quantities, number of moles and molar mass. Since it's not a division, we take it as multiplication. So you multiply them both. That's how it goes. So this triangular diagram actually gives you a great idea on how to cater these three values. If two of them are known and one of them is what you're supposed to find out as a part of the question. Okay, so calculating relative molecular masses or talking about their mass or the Avogadro's number. So it discusses where we're going to get atoms. Of course, it's clearly understandable that atoms are coming from elements. As soon as elements are converted into formulae, and by the way, covalent bonding, it's molecules. Covalent bonding may occur with different kind of atom as well, again molecules. And then we go on with ionic bonding, formula units. Even for covalent bonding, if we have a macromolecular substance, means a giant lattice, even then we're going to use the term formula units. The book clearly explains this whole thing, the whole idea behind putting the word species or particles for Avogadro's constant and for its working. Now, the questions related to moles and mass are given over here too, but I think we have done many more better questions than just these two simple examples. So we now know how to convert moles into mass or mass into mole both ways. We do understand if we need to find out the third one, we also know the formula to that too. Now, apart from these, we are also done with the Avogadro's number and its usage in a formula for moles, which is not clearly explained in the book, but that has been a part of past papers. That's why I gave you a separate formula for it. And lastly, the book defines volume separately, which we are done with, by the way. And I'm going to take you over there, which means I've done the book in a little bit of a different way than what's given in the order of the page numbers over here. So let me take you over there. Okay, 6.4, volume of 1 mole of a gas, molar volume, what the value is, the conversions per liter and decimeter cube or centimeter cube or milliliter, whatever that is. All of that is given over here. Again, the formula. And this is so far what we have done for it. I haven't considered the reactions involving gases yet. So worked example 6.8 will not work for you. Okay, so this is the part which we are done with in the form of some whiteboard work recently. So let's go back. Now, before we can work out chemical equations, we need to work out chemical formulae. Now, in the lab, when we work on chemical formulae, the two types of formulae that we are supposed to face are actually empirical formulae and molecular formulae. Now, I hope you already understand and remember. If not, let's go for a quick memory joggle. Uh, Molecular formulae is actually the type of formula which gives you the exact number of atoms or type of atoms in a formula. This formula tells you everything about the atoms, the types of atoms, number of atoms. And the exactness of this formula is actually what makes it more important than an empirical formula. However, on the other hand, empirical formula is just the simplest whole number ratio of molecular formula. For example, if the molecular formula is H2O for water, the empirical formula is also going to be H2O. For glucose, the molecular formula is C6H12O6. Now, this time, since we can simplify it further, it would become CH2O for empirical formula, since we're talking about a simplest whole number ratio. Now, let me tell you that C6H12O6 can be written like this. We can also write it as C4H8O4. We have simplified it for a little bit more. We can write it as C3H6O3, or we may write it as C2H2O, actually C2H4O2, or simply speaking, CH2O. So there are many ways how we can simplify it. But since I've been using the term simplest whole number ratio, the term simplest itself means that these are all wrong. This has to be converted into the most simple form possible. So glucose would be converted in CH2O and none other formula, right? That's how the simplest formula or simplest whole number ratio between the atoms of a formula is what we define for empirical formula. Okay. Now, let me tell you that all ionic compounds actually have empirical formula as molecular formula. So sodium chloride, the molecular and the empirical formula is going to be the same. Fair enough?
Yes, sir.
All right, good. So what happens is that when we start performing experiments in the lab, then what we find out first is the empirical formula. And there is a proper procedure how we find that out. And then we need to go with the calculations, and these are the calculations explained. We need to convert them into molecular formula. And empirical formula and molecular formula is something that we are supposed to do next in this chapter. So let's go on with that and try to go with different examples of past paper questions explaining how to find out empirical formula, and then later on how to find molecular formula if you're either given masses or percentage composition or total masses or anything like that. So I'm going to stop sharing the book. Let's get to the whiteboard then. So empirical formula. First case. There are different cases that I'm going to discuss. Let's start with the easiest of cases, and then we'll move on to how Cambridge manipulates the question or tries to make it a little bit more difficult. Okay, so the first case is when you are provided with masses of elements. Now, since we are supposed to form a formula, we will be given elements as a part of the question, as well as their masses. For example, let's go with the first example then. Mg and O and 0.24 gram and 0.16 gram. This would be a part of the question, that we do understand that we have been given mass in grams for individual elements. Now we know that our formula is made up of magnesium and oxygen, so is our compound. And we know that in a specific experiment, when we were experimenting what the formula of this unknown substance could be, it turned out that the substance is made up of magnesium and oxygen, and the masses that came out as a result of that experiment were 0.24 grams for magnesium and 0.16 grams for oxygen. Now, what steps are we supposed to do? I'm going to put the solution steps in red so it's easier for you to understand and follow in the same footsteps. Now, first of all, you need to come up with either MR or AR. If you're given a single element, that would be AR, relative atomic mass from the periodic table. Or if it's not a single element, it's a whole compound, since those examples are also possible, we are supposed to take the value of MR. Again, the masses that are given in the periodic table. So the first step, the first lead towards this is to take help from the periodic table. Now, periodic table tells me that the value of magnesium is 24 gram per mole, and the value of oxygen is 16 gram per mole. This is what the periodic table tells me. In the periodic table, I went on to look up magnesium. It told me that the mass for magnesium is 24, and that of oxygen is 16. Are we clear with the first step?
Yes, sir.
If you have a copy of periodic table in front of you, this should be easy. You can easily refer to it. Open up that periodic table, look it up. You'll find that the mass number of magnesium is 24 and that of oxygen is 16. So it's really easy if you have the periodic table copy with you. So moving on, next step would be moles. How to find out moles? Now we clearly understand moles is actually the division of mass over molar mass, right? That was the formula for moles. And we have applied the formula over here for magnesium, and we are going to do the same for oxygen. Now, this would give you the value for number of moles as 0.01 for magnesium and 0.01 for oxygen. There. And do you have the same answer if you're doing it with the calculator? Make sure you keep doing it with the help of a calculator with me. Since I'm not using a calculator,
I don't have my calculator.
Sorry?
I don't have my calculator right now.
Okay, can you go pick it up? You can.
Yes.
Take a minute, go pick it up. That's fine. If you need to pick up your calculator, a pencil, a piece of paper, and a copy of periodic table, that would be great. Go take a minute. I can wait and pick your stuff up. When you're ready, let me know for both of you. Okay, so the number of moles is 0.01 and 0.01 for both the elements, magnesium and oxygen, respectively. I was just saying that, is this answer correct for both of these?
Yes, sir.
All right, if we are correct with both of these, let's move on. The next step would be molar ratio. It is also in some books mentioned as atomic ratio, but that's fine. Both the words, the phrases mean the same thing. Now, a ratio means that we need to simplify these numbers into whole numbers. Now, a way to do that in mathematics, and this is not a step for chemistry, this actually is a mathematical step. Let's say you have three numbers. Let's say you have 0.01, and then you have 0.025, and then you have 0.050. Okay, so you have three numbers. What we do in ratio is that we try to divide all these numbers by the smallest possible number. Let's suppose in all these cases, the smallest possible number is 0.01. So you need to divide all these three numbers by 0.01, and this would give you a very good idea of what these numbers actually mean in molar ratio. So what you would have happen is that you will come up with some bigger whole numbers to give the an easier understanding about what these can be, right? So something like this. But that was just an example to make sure you understand what I'm talking about mathematically. So let's go with what we have in here. So of course, we are going to divide both of them by 0.01 and 0.01. Since both numbers are same, we're going to end up as 1:1. And the last step, if you require a simplification step, you need to go with that. Simplification is a step which is required if you don't still get whole numbers. If you get still numbers with decimals, if that happens, you require further simplification. And simplification means multiplying with a suitable number to get a whole number. But since our numbers are already whole numbers, so we don't really need this step, and we can simply move on to our last step, which is writing the empirical formula. And this is probably one of the only places in the book, not in the chapter, in the entire book. Let me re-clarify myself. This is probably one of the only places in the entire book where we can put or change the subscript. And this is how we do it. Magnesium and oxygen, since this represents magnesium is 1, so magnesium is 1, this represents oxygen is 1, 1, 1. And since we don't write 1, it means the empirical formula is MgO. If these numbers were 2, 2 or 3, 3, it would have been simple. We would have written 2, 2 and then simplify them again. Okay, makes sense?
Sir.
So that's the
Yes,
first
sir.
case. If this makes sense, I guess you can do other examples as well. So let's go with other examples. And since only the name of the elements and their masses is good enough for you to practice, I'm only going to come up with the same pieces of information to get you started. So there is another compound which is made up of just calcium and oxygen, while calcium is 2.33 into 10 raised to power minus 3 grams, and oxygen is also 2.33 into 10 raised to power minus 3 grams. Go ahead, find out what the empirical formula would be for the specific case. And when you're done, you can tell me your answers orally, or you may take a picture of whatever you're doing on a piece of paper and send it to me through WhatsApp. God. So I hope your starting steps were that you put the AR for calcium as 40 gram per mole and that of oxygen as 16 grams per mole, right? And then you divided both of these values and you took out the answer for moles. So the number of moles for both were, what was the answer for calcium after division?
5.825 multiplied by 10 raised to power minus 5.
5.825 multiplied by 10 raised to power minus 5. Okay, and what about oxygen?
1.45 multiplied by 10 raised to power negative 4.
1.45 multiplied by 10 raised to power minus 4. All right, great. Then which answer do you think is smaller out of both of these?
1.451.
That's where you're wrong. 1.45 is not the way how you compare it. You never compare the numbers. You always compare the power of 10. Which one is a smaller number? Does minus 5 is a smaller number or minus 4 is 1? According to a number line, minus 5 is a smaller number. So 5.825 is a smaller number. See? There you go. Now you have found your error. And now I hope you understand you're supposed to divide both of these by this number. All right?
Yes, sir.
So I guess I have given you a wrong question. Let's go on with it. I've given you a wrong set of values, but okay, let's move on. So your answers are, this one is 1, and this one is what?
2.48.
2.48. Okay, which is approximately equal to 2.5. Now, this is going to have a simplification step. Let's go for a simplification step, all right? So this is 1 and this is 2.5 roughly. So you need to multiply the whole thing by 2. This would become 2, this would become 5. It would end up as CA2O5. Makes sense? Although that compound does not exist, I have given you a wrong set of values unintentionally, but I hope you get the point. Well, even with the unintentional set of values, I actually came across a chance to make sure that you understand the simplification process. Do you get it now?
Yes, sir.
Good. What about you, Wes?
Yes, sir.
All right, great. Okay, let's consider another example. Just a minute, let's write it somewhere else. Let's write this example over here. Have some space over here. Okay. There you go. Silicon Si 47 grams, oxygen O as 53 grams. Go ahead, try solving this one up. Again, when you're done, let me know. I'm here.
Is it Si2O5?
It's SiO2. Okay, let's take a look at it. So What's the AR for SI from periodic table?
$28.
28, good. So we are supposed to divide this by 28 and this by 16. Answer to SI was
It was 1.67.
1.67. All right. And what about this one?
3.3.
3.3.
3.3125.
31. Okay, 3.31. So if you divide both of them by 1.67 and 1.67, the answer comes out to be, this comes
For
out
the
to be
first
1, and this comes out to be,
two, it's basically a 1.98, so we will round it.
yeah, this is 1.98, which is rounded off to 2. So this becomes SiO2. How come it's Si2O5? The simplification is only done when you get a number like this one. 0.5, 0.33, 0.4, 0.6, something like that. For 1.98, which is so close to 2, you're going to round it off as 2. Rounding off can be done for any number greater than 1.9 or less than 1.1, which means 1.04 is also 1. 1.99, 1.98, 1.97 are rounded off to 2. That's how it works. And if you stick with something in between, 2.4, 2.5, 2.6, 2.3, you can't round it off. You need to simplify it by multiplying with a suitable number to get you the answer. Now, for the rule of simplification, it is pretty easy. Okay. Simplification. That is, if the number is 0.5, you multiply the whole thing by 2. Okay. 0.33 or 34 are multiplied by 3. 0.25 are multiplied by 4, and 0.2s are multiplied by 5. And I haven't seen more complicated stuff than this. So this is what your point values are usually going to end up as in most of the past paper questions. Not all of those, most of them. And that's how you're supposed to simplify. This is the number you're supposed to multiply it with to get your answer as a whole number. Because if you look at it, 0.5 multiplied by 2 is equal to 1. 0.33 multiplied by 3 is equal to 1. 0.25 multiplied by 4 is equal to 1. And finally, 0.2 multiplied by 5 is equal to 1. So that's how it changes into a whole number from a decimal number. I hope that makes sense. This is more of a mathematical work than it is chemical. Make sense?
Yes, sir.
Any questions so far?
No, sir.
Okay, good. Then just moving on with the second case. Okay. Now, in the second case, what happens is that mass and usually total mass are given. For example, I'm going to bifurcate the whole thing. Let's suppose you are given with given with this, how would you calculate it? Now, the common sense says, since there are three elements and the mass of first two, calcium and carbon, are given as 40 grams and 12 grams respectively, the total is given as 100 grams. Obviously, the mass of oxygen would be 100 minus 40 minus 12. So from there on onwards, you can take the lead. Try doing it by yourself. So this means that whatever I have taught you as a part of calculations for empirical formula previously, you add a zero step to it. And that step is to subtract all the masses from the total mass in order to find out the unknown one. In this case, unknown is oxygen. So total 100 minus calcium and carbon in this specific case, which is minus 40 and minus 12, it would give you the mass of oxygen. From there on onwards, it's piece of cake because it's the similar set of calculations like the previous one. Go ahead. And when you're done with this, let me know. You have a calculator with you? This should be easy. 100 minus 40, it's 48. Good. So we have 48 grams. How do we get it? We just subtracted all the values from 100. So it's 100 minus 40 minus 12. Now, if you have a copy of periodic table, what's the mass for calcium in the periodic table? What's the bigger number you can see with calcium?
So 40.
14, right? For carbon?
Sure, 12.
12. For oxygen?
16.
16, great. So that means 40 divided by 40, 12 divided by 12, and 48 divided by 16. Now, since 40 divided by 40 is pretty simple, so I'm simply going to write it myself. However, the third one is something you need to do with the calculator, and that is 48 over 16. So what's the answer to that one?
Sure, it's 3.
It's 3. So these are easier numbers. I actually came up with a very easy question. There are no decimals, so you can simply take these numbers and form a formula. So what formula do you get?
So we'll divide the smallest digit,
No,
which is
you don't
1.
need to do that. You already have whole numbers. You don't need to do that. Simply create the empirical formula. So we have one calcium, we have one carbon, and we have 3 oxygen. So the formula would turn out to be
calcium, carbon, oxygen 3.
right. That is CaCO3. Easy enough?
Yes, sir.
Good. So if you get a hold of it, I think it's good enough for the day. Any questions?
Yeah. Sir, would it be possible if you can send worksheets related to these questions just for practice?
Okay. I won't be able to send a worksheet later. What I can do right away is that I can write a few questions right here, right now. So let's give you a couple of questions. I think 2 to 3 questions would be good enough.
And I can take a screenshot of them, or yeah.
I am going to send you the pictures right after this class, so no issues.
Okay.
Okay, so I am leaving with you what seems like a very difficult question, but trust me, it's going to be an easier one. Okay?
All right.
It seems like it's difficult because I not just wrote 2 or 3 elements, I actually, to begin with, wrote 4 elements, but it's going to wind up easy. So that's 1.15 grams for sodium. That's 0.05 grams for hydrogen. That's 0.6 grams for carbon. And finally, instead of writing for oxygen, I'm going to write the total so that you can solve a second case scenario question. Okay. And the total is 2.6 grams. Okay. So this was the first example. Give you another. I should a little bit of distance between them. So let me read the values out loud, just to make sure you're getting them right. For hydrogen, it is made up of hydrogen, carbon, and oxygen. And I've made a mistake. Okay, just let me quickly erase it and correct my mistake.
Sir, so in the second example, there is no total given.
Yeah, it's case 1. All the masses are given, there are no totals. Okay, so hydrogen is 2.66 into 10 raised to power minus 3 grams. Carbon is 1.596 multiplied by 10 raised to power minus 2 grams. And oxygen is 6.384 multiplied by 10 raised to power minus 2 grams. Okay, and just for the sake of your ease, let me tell you this is a case 2 question and this is a case 1 question. And obviously, wherever total is given instead of all the masses, it's a case 2 question. And wherever all the masses are given and there is no total to worry about, it's a case 1 question. And since we have learned to solve them differently, I hope you will be able to get them right. Good enough?
Yes, sir.
Great, great. So, any questions before I wind up the call?
No, sir, I'm clear.